In this video, we're continuing our studies of testing a claim about a proportion with normal approximation methods. The p-value method and critical value method that we discussed in learning outcome number 1 were normal approximation methods. In this learning outcome number 2, we're talking about our third and final normal approximation method, which is the confidence interval method. Specifically, we're going to study the confidence interval method here and compare it to the p-value and critical value methods that we studied in the last learning outcome. By the end of this video, my hope is that you'll be able to test a claim about a proportion using the confidence interval method. I'll also want you to be able to explain why the confidence interval method does not necessarily lead to the same conclusion as the critical value and p-value methods. So here's an outline of how that method works. We can use the confidence interval method provided that the requirements for using a normal approximation to the sampling distribution are met. So here's our first requirement. The sample data must form a simple random sample. Now, back in chapter 1, we talked about simple random samples and random samples, but we didn't differentiate between the two too much. If you are a future social scientist or you are a scientist and you're using these methods, you really should be able to distinguish between that simple random sample and random sample. So if that's you, I would suggest, I'd highly recommend that you go back to chapter 1 and look at the finer points, the differences between those two terms. Now, for most of us, whenever we are checking this requirement just for the purposes of this class, the distinction between simple random sample and random sample isn't too important. I will typically assume that this requirement is satisfied if I see randomly selected in the problem statement, if I see random sample in the problem statement. Even if I don't see one of those phrases, I will assume that I have a simple random sample if I don't have a reason to assume otherwise. So if it doesn't seem that the data are from a voluntary response sample or a convenience sample, I will assume that we have a simple random sample and qualify my conclusions by saying that this is based on that assumption. If that assumption happens to be false, the conclusions shouldn't be used for other purposes. Okay, so that's the first requirement. The second requirement is that the requirements for a binomial distribution must be met. The first is that we have to have a fixed number of trials. Now, the number of trials typically is the same as the sample size. So each, let's say, individual that you're surveying, if you're talking about a proportion of individuals believing some idea, each individual constitutes a trial. So as long as we're keeping that sample size fixed, the requirements for a binomial distribution are met, or at least that first requirement is. And the second requirement is that each trial must have exactly 2 outcomes. Typically, those are called success and failure. Now, success does not necessarily have to be positive. Failure does not necessarily have to be negative. If we're saying, we're asking people if they prefer Coke or Pepsi, we might say preferring Coke is success and not preferring Coke is failure. It doesn't mean that we prefer Coke to Pepsi ourselves. So it really just depends on where we have placed that label. And once we have chosen that label to go with a certain outcome, then we just need to be consistent with that. So every trial has to have exactly 2 outcomes. It can't have 3 or more outcomes. So if we've got 3 or more outcomes, we've got to do something else. This is then, in that case, we wouldn't have a binomial distribution. The third requirement for a binomial distribution is that the trials must be independent. All that is saying is that the probability of success in one trial cannot depend at all on the probability of success in other trials or the outcomes of other trials. If the outcomes of other trials or the probabilities of other trials are dependent on this particular trial or a particular trial, those trials are dependent, not independent, and then the requirements are not met. But if the outcome in one trial is not at all affected by any of the others, we say that those trials are independent. And lastly, the probability of success must be the same in each trial. Typically, we assume that this is satisfied. If we have some reason to believe that the probability of success changes from trial to trial, then this binomial distribution would not be appropriate. And then lastly, if we have a simple random sample and all of the requirements for binomial distributions are met, we need to have at least 5 expected successes and at least 5 expected failures, given the assumption that the null hypothesis is true. Now remember what the null hypothesis will say. This is going to say that the population proportion, or the probability of success, if you prefer to look at it that way, is equal to some value. So when we say we have at least 5 expected successes, that means if we take the number of trials, n, and we multiply by the probability of success in one trial, which is the p stated in our null hypothesis. So that's the p that we're assuming in our null hypothesis. If n times p is greater than or equal to 5, that means we have at least 5 expected successes. To say that we have at least 5 expected failures is to say that the number of trials n times the probability of failure in one trial, given the assumption that the null hypothesis is true, which is q, where q is 1 minus p, the complement of that probability of success. If you take those, the n and the q, and you multiply them together, and you get a number that's greater than or equal to 5, what that means is that we have at least 5 expected failures. Provided that both of those are satisfied and the requirements for the binomial distribution are satisfied and we have a simple random sample, the requirements for using a normal approximation to the sampling distribution are met, and we can use the methods that we talked about in the last video, the p-value method and the critical value method, and we can also use the confidence interval method that we're talking about in this video. Okay, so if the requirements are met, then we will compute a confidence interval using the formulas from chapter 7. Now remember, back in chapter 7, we said that if we're trying to estimate a population proportion p, we compute p hat, which is a sample proportion. That's the number of successes divided by the number of trials in a particular sample. And then we're going to add and subtract the error from that, where the error is equal to z sub alpha over 2 times this expression here. Now z sub alpha over 2 is a number of standard deviations above the mean, and it's a z-score, that separates that top alpha over 2 area from the rest of the area under the curve in a standard normal distribution. And whenever you're doing a confidence interval, it's always sort of two-tailed in the sense that you've got alpha over 2 area in the right tail and alpha over 2 area in the left tail. Z sub alpha over 2 is just the z-score that separates that alpha over 2 area in the top right tail from the area in the middle. And that area in the middle corresponds to z-scores, and those z-scores correspond to values of p and p hat. We got into more of the details, the nitty-gritty of that when we talked about confidence intervals back in chapter 7, so you can look at that as well. But I just want you to know that z sub alpha over 2 is a z-score that separates that alpha over 2 area at the top. So that's the z-score. Now if I take the z-score and I multiply by an approximation of the standard deviation, that's giving me the error. So it's giving me sort of a number of standard deviations from p hat, kind of. It's just, we have to remember how this was constructed. You should really look at those videos to see where this confidence interval comes from. Now this expression that I circled is an approximation of the standard deviation of p hat. I'm sorry guys, I'm trying to find my mouse again. For some reason it's been acting up lately, and it's making it hard for me to see my mouse as I'm doing my work. Oh, okay. Sorry about that. Having a lot of little tech issues lately. Don't know what's wrong with all of my devices. Just cursors disappear all the time. Okay. All right, so now I've got my mouse back. So this yellow expression that's circled is an estimate of the standard deviation of the sampling distribution of p hat. And notice that it has a square root of p hat times q hat, where p hat is the sample proportion and q hat is 1 minus the sample proportion. It's going to be important later. So you use these formulas and you're able to calculate the confidence interval. It came from looking at that sampling distribution of p hat, coming up with an inequality that had p hat in the middle, and then taking that inequality and then solving it for the population proportion p, which was unknown to us. Okay, so after you've computed that confidence interval, we want to use it to make a decision about the null hypothesis. The null hypothesis says that the population proportion p takes on some value. If p lies in the interval, that tells us something. If p doesn't lie in the interval, that also tells us something. So that's going to help us make this decision about the null. If the value of p assumed in the null hypothesis is in the confidence interval, then we're saying that that value of p is likely to occur. We expect p to take on one of those values. We have a certain level of confidence that p lies in that interval. So if the assumed value of p lies in that interval, we're going to say, okay, well, that p could take on that value. So in that case, we're going to fail to reject the null because the fact that p lies in that interval suggests that the null hypothesis might be true. Now, if the value of p from the null hypothesis is not in the interval, that's saying that p is not likely to take on the value in the null hypothesis. So if p is not likely to take on that value, then we're going to reject the null hypothesis. And then, of course, we always want to state our final conclusion in terms of the original claim in words everyone can understand. No one should have to know what a null hypothesis is, or a confidence interval is, or a p-value, or an error, or a z-score is in order to interpret our results. Okay, so let's look at an example. So the problem statement says that some claim that the majority of consumers are not comfortable with drone deliveries. In a survey of 1,009 randomly selected consumers, 545 of them were uncomfortable with drone deliveries. The question asks us to test the claim with a 0.05 significance level by constructing an appropriate confidence interval. Okay, the first thing we need to do anytime we're doing a test of a hypothesis or a test of a claim is come up with the null and alternative hypotheses. So first we identify the claim. It's at the very beginning here. It says that the majority of consumers are not comfortable with drone deliveries. So the majority, that means that the proportion is more than 50%. So the claim is that p is greater than 0.5. Now, since that has a greater than sign, which does not contain the condition of equality, that's our alternative hypothesis. Now, the null hypothesis always looks exactly like the alternative hypothesis. But instead of having a greater than sign, a less than sign, or a not equal to sign, it just replaces the sign with an equal sign. So our null is that. Okay. Once you have the null and alternative hypotheses, then we want to determine whether the test is two-tailed or one-tailed and find the area in one tail. Then we can use this to infer the confidence level. Now, with confidence intervals, there are always two tails. Whenever you're looking at that error formula, you always have that z sub alpha over 2, where alpha is the area in two tails with a confidence interval method. We're using alpha differently whenever we use the p-value method or the critical value method. Alpha may be the area in one tail if we have a left-tailed test or a right-tailed test in that case. Alpha over 2 may be the area in each tail if we have a two-tailed test. So what we need to do in order to use the confidence interval method appropriately is find out whether the original test, the hypothesis test that we're conducting, would have been two-tailed or one-tailed, and then we want to find the area in one tail given the nature of the hypothesis test. Once we know what the area in one tail should be, we're going to double that to infer the confidence level associated with our confidence interval method. Okay, so we look at the alternative hypothesis and we see that we've got a greater than sign. We can think of this as an arrow that's pointing to the right. So we've got a right-tailed test because the arrow points to the right. Now, if I have a right-tailed test, that means the area in the right tail is equal to my significance level, or 0.05. So I need that upper area in that right tail to be 0.05. Whenever we come up with a confidence interval, the area in the tails needs to be symmetric. Even if the area in the tails was not symmetric when we were using this one-tailed test with the p-value or critical value methods, it's always two-tailed for confidence intervals. So if the area in one tail is 5% and we're using a confidence interval, well, I need the area in the top tail to be 5% because we've got a right-tailed test with a significance level of 5% or 0.05. And I also need the area in the left tail to be 5%. So I've got 10% of my area in the tails. That means I've got 90% of the area in the middle. So I want a 90% confidence level. So in this case, I use this formula. My alpha value was 0.05 and it was a one-tailed test. So I double it and I subtract it from 1 and then I multiply by 100% to get that 90%. Now, most of the time I'm not actually using that formula. I'm just converting that significance level to a percentage, like that 0.05 is 5%. And if it's a right-tailed test or a left-tailed test, I double it and subtract it from 100 to get the level of confidence for my confidence interval. If it's a two-tailed test, the area in the tails, both tails, is equal to alpha. So in that case, I would have 1 minus alpha here instead. But the idea here is you just want to know how much area should be in the tails so that you can find out how much area should be in the middle. If 10% of the area is split between two tails, then we have a 90% confidence interval, which means we've got 90% of that area in the middle. Okay, so now I want to construct that confidence interval at a 90% confidence level. I'm not going to review this with you, but you're just going to use those formulas that were shown a few slides ago. If you need to review how to construct a confidence interval, go back to the videos and notes, for lesson 7.1. That's where we discussed finding confidence intervals for population proportions. So using the methods of 7.1, we can find this confidence interval. It turns out that P is equal to 0.514, or P is between, 0.514 and 0.566. And so what we're saying is, whenever we come up with this confidence interval, that we have 90% confidence that the value of P, the true population proportion, is between 0.514 and 0.566. We're not saying that P is equal to P hat, the center value in that interval. We're not even saying that we're 90% sure that P lies in that interval. What we're saying is, if we were to construct, let's say 100 confidence intervals, 90% of the time, the true value of P would lie in the interval. So this interval of values is giving us values of P that we would expect to find. There's really only one true value of P, and we're saying that we expect it to be in this interval. If we do this process over and over again, 90% of the time, P will be in an interval that looks like this. Okay, so you might need to review how to come up with that. If necessary, go back to lesson 7.1. For right now, in this video, we're just going to focus on interpretation. So we see that interval, and we remember that our null hypothesis is that P is equal to 0.5. That's going to allow us to decide whether we should reject the null hypothesis or fail to reject the null hypothesis. That interval will allow us to decide that by just looking at the interval and seeing if P equals 0.5 is in the interval. Since P equals 0.5 is not in the confidence interval, we're saying that P equals 0.5 is not a p-value that we would expect to have. That range of p-values is between 0.514 and 0.566. The lower bound is above that P equals 0.5. So we don't have evidence to suggest that P could equal 0.5. So we're going to reject the null hypothesis in this case. And then we want to state the conclusion in terms of the original claim. That requires looking at the original claim Now, our original claim was that P was greater than 0.5. So our alternative hypothesis in this case happened to be the claim. So when we reject the null hypothesis, in this case, we are supporting the alternative hypothesis, which happens to be the claim. So rejecting the null means we're supporting the claims. That means we have sufficient sample evidence to suggest that the claim is true. So one way that we could state this is that there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone delivery. So that's how we would do that test. But again, review how to come up with that confidence interval if you need to, using the materials from lesson 7.1. Okay, so now let's talk about equivalent methods for testing claims about proportions, or methods that aren't equivalent, to be more exact. When we're testing claims about proportions, I want you to be aware of the fact that the confidence interval method is not equivalent to the p-value method and critical value method. The p-value and critical value methods are equivalent. They're always going to give you the same results, but the confidence interval method sometimes gives you a different result regarding the null hypothesis. There are times when the p-value and critical value method will tell you to reject the null, or the confidence interval method tells you to fail to reject the null, or vice versa. Many times they agree, but we're not guaranteed that they agree because these are not equivalent. And if you're saying, why aren't they equivalent? The reason they are not equivalent has everything to do with the standard deviation that we're assuming when we use these, or when we use formulas in the p-value and critical value methods and the confidence interval method. Now with the p-value method and the critical value method, we're using the same standard deviation based on the claimed proportion P. So that's the P from the null hypothesis. So in both of those methods, we're coming up with a test statistic Z, and Z is the number of standard deviations that P hat is above the mean, given that the mean of P hat is equal to the population proportion, and that population proportion is the value assumed in our null hypothesis. So really, when I'm looking at this, I'm focused on this denominator. See that standard deviation there? And that standard deviation there? Those are the same. So this is the standard deviation of P hat. Notice it has the square root of P times Q over N. P is the value of the population proportion assumed in the null hypothesis. So we're assuming that the null is true, and then we're creating the sampling distribution. Okay, try to get my cursor back again. Having a lot of trouble with this lately. There we go. Okay, now let's look at the confidence interval method. Well, the confidence interval method, we aren't assuming that we know the population proportion P. We are, we're not assuming that. What we end up doing whenever we're using the confidence interval method is we come up with this inequality, and that has P hat in the middle. And then we solve that inequality, or we rearrange that inequality so that the population proportion P that we're looking for is in the middle. So there is no assumption about the null hypothesis here, or excuse me, there's no assumption about the value of P here. We're using a range of values for P hat to infer a range of values for P, or using an interval for P hat to infer a range of values for P. So notice that whenever we came up with these formulas, the standard deviation that we're using, the approximation of the standard deviation, oops, sorry about that. That's this right here. I keep trying to do it. I'm having a really hard time with all of my technology lately. Everything is being a little bit buggy, and that is okay. We can roll with the punches. Sorry about that. I'm gonna try again. Okay, there we go. Now, whenever we are looking at the confidence interval method, we've got this z sub alpha over 2, which is a number of standard deviations above the mean. And we're taking that and we're multiplying by this expression that I've circled in yellow. This is an approximation to the standard deviation, and it's based on the sample proportion. Notice the difference between that and the one that we are using for the other formula. I'm sorry, guys, I don't want to waste your time with this, but for some reason, my computer has been acting up a lot lately, and things that are normally work just fine have been disappearing on me. But that's okay. We can always work with it. We always do the best we can with what we've got. Okay. All right, so there's some weird stuff happening again. I'm sorry, guys. I don't want to have to remake this entire video, and I don't know enough about video editing to edit this out. So you guys are going to get to watch while I make these, while I have trouble trying to get my mouse back. I wish I understood why all of my computers were acting up and being so buggy lately. Okay, so I don't know if I'm going to be able to circle what I would like to circle. There it is, it's going to work again. So that's the other standard deviation that I was trying to point out. With the confidence interval method, the estimated standard deviation has a p-hat in it. And with the p-value and critical value methods, we are using the standard deviation that is based on the assumption that the null hypothesis is true. So it has the p from the null hypothesis in it. So the confidence interval method and the p-value and critical value methods are using a different standard deviation. And since they're using a different standard deviation, there's a chance that a p-value that lies in the confidence interval doesn't lie, or it does not satisfy the requirements for the p-value method or critical value methods. We might come up with different conclusions based on the first two methods as opposed to the last method. So just know that the critical value method can give you a different conclusion than the p-value, or excuse me, the confidence interval method can give you a different conclusion than the p-value and critical value methods. But the p-value and critical value methods always give you the same answer because they're using the same test statistic. Okay, gonna try to get my mouse back again. I apologize, this must seem very unprofessional, but someone, I don't know why, but my computer has been very buggy lately. Lots of little problems with my computer. Trying to get my mouse back. All right. Sorry about that. Thank you for your patience. Okay. So we said that those three methods are not equivalent. The last two are equivalent. The confidence interval method is not. And here's the recommendation. Confidence intervals should be used to estimate a population proportion because they are based on assumptions about p-hat, but they're not based on assumptions about the population proportion itself. That's why the standard deviation that we're using in the confidence interval derivation does not include a population proportion, because we're trying to figure out what the population proportion is. But with the p-value method or critical value methods, we are assuming a value for the population proportion. And by assuming that value, we are also assuming a value about the standard deviation of the sampling distribution of p-hat. So we're going to get two different results. And I recommend that you use the confidence interval method, or not method, but the confidence interval to estimate a population proportion. It's constructed in order to estimate a population proportion. And then you use the p-value and critical value methods for testing claims about proportions.